We now move on to the second part of this first topic of introduction to the studies of dynamism of coastal spaces using remote sensing. In this second part, we will focus our attention on the scales at which morphosedimentary processes occur and the geomatic techniques that are applied in coastal studies. Coastal morphosedimentary processes are extremely complex, and they involve different agents that interact on different spatial temporal scales. Thus, there are immediate physical actions taking place on a metric scale, or even more detailed, such the continuous movement of the sand associated with the swaying of the waves, which contrasts with changes in the position of the coast caused by the progressive displacements of tectonic plates that affect large terrestrial regions and that stretch over thousands or millions of years. However, those changes that can affect more immediate to the societies are undoubtedly of the mesoscale, that is to say, time lapses ranging from days to decades and geographic area ranges from tens of meters to hundreds of kilometers. The coastal studies on these spatial temporal scales will contribute indispensable keys for the proper management of coastal areas. That seeks to ensure the sustainability of these environments and minimize the risks to the societies that inhabit or enjoy them. To analyze these processes and the changes that occur on the coasts at these spatial temporal scales, it is especially useful geomatics techniques and remote sensing. The graph on the right shows some of the techniques on the analytical scales we are working on. And as you can see, the observation of the Earth from satellite covers a very wide space-time range, which evidences their high potential in this type of studies. The advances of the different geomatic disciplines and techniques. In the last few decades, they have been a real revolution in the form of recording coastal morphology. Topobathymetric surveys using DGNSS systems allow to acquire data 3D with a very high precision. The use of photogrammetric solutions both from drones and from fixed cameras that record continuously changing on a beach, that we call video monitoring, it is facilitating the mass acquisition of information by 2D and 3D. Also, the widespread use of LiDAR or obtaining modeling three-dimensional obtained by photogrammetry allow quantify the volumetric changes that actually occur on the beaches. This example shows how three-dimensional changes can be quantified in a stretch of beach after the passage of a great storm. Digital surface models of 1 meter resolution, they have been obtained from photographic series acquired in the summers of 2019 and 2020. Shaded images allow you to recognize the recession suffered by the dune front. Watch the stairs of the walkway that crosses the dune, where the black line is indicating the position of the topographic profile, and compare with that we see on the left. With that data, you can calculate the volumetric changes suffered between these two dates. If we are looking to analyze the changes over a relatively long period of time, it will be necessary to focus attention on some key indicator. Most commonly used in studies of coastal evolution is, without doubt, the shoreline, that is, the line that separates the water from the land. This position changes as beach morphology does and therefore has become an essential indicator and highly efficient, especially on microtidal beaches. If we relate the shoreline to the inland edge of the beach, we'll get the width of the beach, which is a parameter key to indicate the state of a beach and to deduce its load capacity, that is, how many people fit. The shoreline can be easily detected using multispectral imaging, thanks to the huge difference in reflectance between land and water when we analyze it in infrared bands. And with this we end this second part.